This brings us to the last one to take care of, is the universal gravitational potential energy. So let's first think about which work done. So this is the work done of moving objects closer. So which work done formula or definition should we use, the simplest or the more complicated one? Now we need to see if the force is constant or not. Now, as they move closer and closer together, it depends on the distance, right? So remember, the force is gm m over r squared. So as they move closer and closer, then, so if you try to move them, let's say this guy moved towards here, so that's the displacement. Let's say, yeah, a tiny displacement in this way. The force is this way, all right, good. So they're in the same direction. But the force changes. The magnitude of the force, as you can see, gets larger and larger. The smaller this is, the larger the attractive force, right? The further away, the weaker the gravitational force is. So the force is changing. You need to use, unfortunately, the most complicated version. So from initial to final. Now this raises a question: what initial to what final? Well, it doesn't matter, because really the change is, we really care about the change of the potential energy is what gives the change in kinetic energy, right? Remember, ultimately we care about motion and we want to predict the final state of things, and you're going to use this formula. So you don't really need the absolute energy. We can define that, and that is slightly beyond the scope, but we can easily define the change in potential energy, okay? And we need to use this, okay? So you can see they are, first of all, they are parallel. So they're moving in this way. So the gravitational force is in the same direction as the displacement they're moving. So we can easily take the dot product and just change it into this, okay? And we will use the gravitational force this time. So that's gm m over r squared dr. And these are constants, so we can pull them out. Okay, and if I write this as r to the, if it's 1 over r squared, if that intimidates you, right? So you can rewrite that as r to the minus 2, and now you can just use the power rule, right? So you remember the power rule is to increase the power by 1. So it's minus 1, and divide by the new power. So new power is minus 1. And then put in the limits of initial to final. Okay. Yeah, so that's really just, if I rewrite that, right, that's negative 1 over r. Okay, so I'll put in final minus negative 1 over r initial. Right. Okay, you can check that if I did it the right way around. So that is, what is that? So the positive is there. So we'll have negative RF minus negative GMM over RI. Okay. As you can see, so this is, so what we can do is now we can associate that with UF and that with UI. Okay, so because that's the change, it should be final minus initial. So what does that tell me? So U at a given distance apart, right, will be minus GMM over R. That gives us the final result as well. So you can see really these formulas that we quoted, but the ones that we will use, right, MGH, probably 90% of the time we'll use that. The other 5% of the time we'll use this, and the other 5% of the time we will use this. And all these didn't sort of magically get pulled out of the hat, but there's a reason to that madness. It's really defined through work done. It's the work done by gravity to move a certain distance, like that. Okay, the absolute, to get this, there's the more rigorous way to treat this, but that's slightly beyond the scope of this course, and we'll just be content with just looking at the displacement of this. So sorry, the difference between this. Okay, so there's only one last thing to wrap up in this chapter, and that's power, and that's a pretty easy and straightforward concept, and we'll summarize that in the last video.